Hello dear students. Today we will be discussing related to errors in moving an instrument and PMMC instrument. So first we'll go through the various errors that occur in moving an instrument. So there are two types of errors which can be classified into something like which occurs in both DC and AC, and then errors which are only for AC measurement. Now the first one is hysteresis error. So this hysteresis error is available, or it occurs while we measure both DC as well as AC currents. Now, so this is your general hysteresis loop that you must be knowing. So this is B H. So this is your hysteresis loop. So this hysteresis curve basically gives a relationship between the variation of magnetic intensity and the flux density, or it can be also plotted between phi and I, the current varying and the flux. Now what happens is that if you are considering the case of an AC, you will be following this outer path. Once it is magnetized, you will be following the outer path once for every cycle. So for 50 cycles we will be following this path for demagnetization as well as demagnetization of your magnetic field. Now during the positive half cycle it will be increasing like this, then reaches the peak and then it reduces. And when the current reaches 0, your flux density will be reversing and it will have a negative value when you move this way. So you'll have such a variation. So what you can understand is that with the variation of current, cyclic variation of current, your flux density is not remaining constant, but it also varies in a cyclic manner with positive as well as negative values, or in both the directions. So such an error will cause such a variation will cause error in the magnetism that is produced as well as uh, the readings that are being provided. Now in the case of a DC, what happens? Suppose you are measuring 5 amperes. Now you are changing the value of the current that is flowing from 5 ampere to 6 amperes. Now during this variation your flux density varies. Okay, so during this variation you will have a change in the flux density. You will have a continuous variation of current, also you will have a continuous variation of flux density. So that variation of flux density will be affecting the readings. So you have such errors happening in the system. So what you can do is you can choose instruments which are having minimum hysteresis loss or minimum area of hysteresis curve. So something like this, you can choose magnetic materials of this nature which reduces a hysteresis loss or which has minimum variation during the change of current or change of intensity, magnetic intensity. So such materials could be chosen. Now the second one is the temperature error. Now the temperature error affects the instrument in two ways. It affects the springs and the magnets. It affects the coil which is being wound as the fixed coil. Now in case of springs, what happens? As the temperature increases, the springs will be expanding, and in case of magnets, the permeability will be affected. The net effect is that the meter will be indicating a higher reading. Now in case of copper coil, as the copper coil expands, as the temperature increases, the length increases, and it will be directly affecting the reading. As the length increases, resistance reduces, so you'll have a different reading. There will be a change in the resistance. So resistance increases, your R is proportional to L, so resistance increases and you will have a difference in reading. Now this effect is more prominent in case of voltmeters. In ammeters, what you can see is that the current will be directly flowing through the coil. Okay, so the current is flowing, and if the resistance increases, the coil resistance increases, it will be affecting the voltage drop across the coil. Okay, still you can send the current through it, there is no issue with that. About the voltmeter, once the MI instrument is used as a voltmeter, you are connecting it across your load. Suppose this is a load and you are having a voltmeter. Okay, so once the resistance of the voltmeter increases, uh, the current that is flowing through this voltmeter will be affected. Okay, so since the resistance seen by this parallel uh, uh, path will be changing, so the current that is flowing through the voltmeter will be reducing, and that will be affecting the overall reading of the meter. So in case of voltmeters, what we generally do is that you will be connecting a series resistance, which is known as a swamping swamping resistor in series with the coil, in series with our fixed coil. And the property of this swamping resistor is that it has very small temperature coefficient of resistance. That is, the variation of resistance with respect to temperature is very minimal, and you generally make use of materials like magnet. Now, once we connect this in series, the overall resistance variation with respect to temperature will be minimal. Normally, your copper coil will have, suppose, a resistance variation of 0.02 percentage, suppose, per degree Celsius. Okay. Now the magnet will be having very minimal resistance. When you combine them together, the net change will be change of resistance with respect to temperature will be very less. You can take some practical example and take two values and compare with and find out the change. That can be done, and this can be proved. Now, the next type of errors include the stray magnetic fields. As we know, we don't have a permanent magnet system available in MI instrument, so the magnetic fields which affect the working of the instrument from outside will cause a demagnetization effect. If the external magnetic field is opposing the magnetic field that is already being produced by the fixed coil. So this can be minimized by providing a shielding, ion shielding over the working parts. Then you have another type of error, which is your frictional error. So this frictional error can be minimized by choosing proper mechanisms, which reduces frictional errors. Like you already have dual bearings. Okay, so these dual bearings has to be designed and chosen in such a way that you can reduce the frictional errors. Again, temperature also will be affecting this dual bearings to some extent, so that also can be reduced by properly designing your such elements like dual bearings and such elements. Okay, so such errors also can be reduced during the manufacturing process. Now there are some errors which are associated with AC only. So we have frequency error due to variation in frequency. Now this variation in frequency affects the meter in two ways, instrument in two ways. One is you'll have a change in the reactance of the working coil. You are using the same instrument to operate at different frequencies, so that will be affecting the reactance of the working coil, and we have already seen how the frequency is going to affect the reactance and how we are going to reduce such effects. So we have already designed shunt and multipliers by neglecting or in order to reduce the effect of frequency. So such additions or such modifications can be made in order to reduce the change in reactance of the working coil due to change in frequency. Again, the eddy currents that is set up in the metal parts of the instrument also affects the readings. You have metal vanes available. Okay, so since these metal vanes are under the influence of magnetic flux, you will have eddy currents generated in this metal veins to some extent. It is not a large error, but some errors, some eddy currents, small magnitude of eddy currents will be produced. So such eddy currents will be opposing the movement, and small errors will be introduced due to this. And this is due to the variation of frequency or change in frequency of your uh, the quantity that is being measured or the current that is being measured. Now the advantages of moving instruments uh, are several. These are highly recommended for many applications. These are used in both DC as well as AC circuits. They are robust and simple in construction. They have high operating torque since you are directly able to send current through the working coil or the fixed coil. They can also withstand overload momentarily because you have a fixed coil which carries the current, so that fixed coil is having some overload capacity. Now they are uh, simple and cheap. They are suitable for low frequency and high power circuits. low frequency and high power circuits. When you move for high frequency circuits, you will have some errors introduced which can be minimized. Again, these are capable of providing accuracy within the limits of precision. When you think about the precision, they are highly precise instrument. They are able to provide accuracy within the limits of the precision as well as industrial grades. Now, industrial grade instruments are expected to operate in highly accurate manner in both DC as well as AC ranges. So these are excellent choice since both AC and DC can be measured. And compared to compared to PMMC instruments, the errors are higher. And if you are not requiring accuracy levels, very high accuracy levels for measuring DC, you can go for MI instruments. If you are going for highly accurate measurements, you can choose PMMC instruments. Now the scale is not uniform. This is one of the disadvantage. The scale is having a non-uniformity at the starting and the towards the end. Now when you are using as a voltmeter, your power consumption is higher for low voltage range because you will have a fixed resistance. Once so this is suppose the load that is measured. So this is your meter, this is the voltmeter. Now the voltmeter resistance is fixed. Now if you are going to have a low voltage being measured, suppose the voltage across this is low, the current that is flowing through this resistance also will be small. So your voltage drop across the this will be higher, as well as the power consumption is higher, because power consumption is related to the current that is flowing, I squared R. So that the power consumption is also higher if you are going for low voltage measurements using a particular meter. Now you have some errors due to hysteresis in the iron of the operating system and due to stray magnetic fields, which also can be minimized. Frequency variations causes some errors in the instrument, and the temperature effects also causes some errors. So basically what you can summarize is that in case of errors, MI instruments are having higher errors when compared to PMMC instrument. If you are going to make a comparison, if you are going to measure DC using both the cases, errors will be more for MI instruments. And so those errors inherently form the disadvantages for this particular instrument also. Now moving on to some errors in PMMC instruments which were not discussed earlier. The main errors are frictional error that we have already discussed in MI instruments. So you'll have some frictional error in the jewel bearing section. Okay, so you'll have the pivot, so you'll have some errors in the jewel bearing. Then you have the permanent magnets available. So due to aging of the permanent magnets, the flux density reduces, which reduces the deflection torque, and hence the reading will get affected. And due to aging, what happens? Aging of springs. The springs aging causes the stiffness of the springs to increase, which reduces the controlling torque and inherently increases the reading that is being produced. So the permanent magnets, aging of permanent magnets reduces the reading, and aging of springs increases the reading. Now due to temperature variations that we have already, very similar to MI instruments, we'll have temperature variations in springs and magnets, as well as the copper coil that is being used as the working coil. Now in springs and instruments, springs and magnets, the reading increases by 0.013% per degree Celsius increase. And if you are having no compensation, inherently the copper will be due to the variation of temperature, the resistance of the copper will be increasing, and that causes the reading to decrease by some value. Okay, now you are using some swamping resistance in series with the moving coil, and this swamping resistance will balance the effects due to temperature variations. Now you can see that the reading is increased here. Okay, and the reading is decreasing here. So this inherently balances. Still you have some higher error due to the change in temperature at the copper side. So that can be balanced by using swamping resistance. So this magnetic will be balancing the effects of due to temperature variations. Now the stray magnetic field errors can be reduced using shielding of the iron parts which are available using an iron case. Now the last one is a thermoelectric effect. So these are generally occurring in shunts due to unequal heating. Okay, so this due to unequal heating, what happens is that the temperature difference, the increase in temperature at the shunt as well as at the working coil or the moving coil will be different. So because of these temperature variations, there will be uh, uh, some voltage being produced due to Peltier effect. So which again can be minimized by mm, uh, giving um, giving connecting the shunt using some particular materials. Okay, and these are very small effects, small errors which are generally neglected. Still we have such an error available in the system. Now these errors can be minimized by using alloys like Magnanin and Constantan, which has a minimum variation of temperature when compared to the copper. In comparison, the temperature effects will be minimum if you are using Magnanin or Constantan as the shunt element. So such choices can be made in order to reduce the thermoelectric error. These are basically occurring in at the shunts and multipliers which are used to extend the range. Okay. So these are general discussion regarding the errors in MI as well as PMMC instruments. Thank you.